So to count the zeros in a box, we did this. You did these exercises for the not exercises. I mean, you must have seen this. The capital N in a rectangle. How many zeros are there? Did you do this with them? The number of zeros of zeta S in a box. No, they didn't do it. Okay, so in a rectangle, like, so can you prove this? Show that if chi is primitive, modulo q, and n t chi is the number of zeros in the rectangle so sigma is greater than 0 and less than 1, and little t is less than t. No, not show that. Let chi is a primitive character be mod q, and nt chi is the number of zeros in this rectangle. So can you show that? Nt chi is equal to t by pi log qt by 2 pi minus t by 2 pi plus big O of log qt. And here t has to be at least 2. So if you have not seen the proof for the Riemann zeta, then you can also do this for the Riemann zeta. I mean, I don't mind. It's about the same. It's not so different as a proof. So can you make an attempt to prove this? So you will use the functional equation and the completed zeta function or L function as you like. Can you think about it for a while? Do it for the simpler case, but it's not very different. The proof is more or less the same. Please repeat.
Think about that counter integration.
Yeah. Yeah. You have to do a contour integration, but you have to take a rectangle.
That's on that rectangle.
Okay. Do you want to do it on the board? Try. First try it on paper, then you can come to the board and try to do it. So what do you want to do? Do you want to do it for zeta or do you want to do it for L function? I mean, it's not so different. Like if you do it for zeta, then just this chi will not be there. You'll just have n of t. Yeah. The number of zeros of zeta s. Yeah. You can think of it like that. Nt. In that case, it would be n of t is the number of zeros of zeta, okay? in the rectangle, and then you can show this. There'll be no Q in the story. Yeah. So and then also you don't, so I don't mind if you do it for NT chi or if you do it for NT, it's essentially the same thing. There is no big difference. You include the 0 inside. Yeah, when you make your rectangle, you have to include the 0 in it. If you have the Riemann zeta, then there's no problem. Yeah, that the extra 0 is not going to come. Just that, which rectangle do you suggest? Yeah, but yes, of course that rectangle, but you want to have a contour, right? Something like that. So which points would you like to take here? If you are working with the L function, then you should take a bit larger one. If you are working with the zeta, then you don't have to. So, so I will take a rectangle R with these points, 5 by 2 plus IT. Okay, 5 by 2 is just a little bit bigger than 2, 2.5. You could have taken something else. 5 by 2 minus IT, then minus 3 by 2, which is just 1 plus half, negative of 1 plus half, and plus IT, and minus 3 by 2 minus IT. Okay, so if you take these 4 points, this should include, if you take, let R be the rectangle, let R be the rectangle with these vertices. With these vertices. Okay, so do you, why take, I mean, you could have taken something else. This seems to be an easy thing. This is 5 by 2 means I'm at, say, 2, little bit more than 2. Yeah, so 1, 1, 2, 2.5. Okay, say here 5 by 2 and plus IT and minus IT, and minus 3 by 2, minus 3 by 2, so it should be, yeah, my drawing is not very good. It's not going to be, so it's going to be, this is plus 5 by 2, so plus IT somewhere here, and minus IT somewhere here. That's okay. And then I have minus 3 by 2, so 1 and 1.5, say here. So minus 3 by 2 plus, yeah, something like that. 1, 2, 5 by 2, and 1 minus 3 by 2. Yeah. So this will include this. So I make it a little bit bigger. Why I move a bit to the side is because I want to include a possible 0 at s equal to minus 1. Yeah, this one I want to include. Okay. I'm going to include this. When we do this for Riemann zeta, I don't have to do this, but here now, this time I'm taking it a bit larger. Okay, and so how many zeros can this one have? How many trivial zeros can be here? How many trivial zeros do you expect? Is it possible to have in this rectangle? How many trivial, not non-trivial? How many trivial zeros can there be? At most one. And where? Either it can be at 0 or at -1. Yeah. There can be. So there can be. So this is RB, the rectangle with these vertices. So it contains this remark. The rectangle is chosen to include a 0 at s equal to -1. Yeah. All right. And now all right. So what are the trivial, how many trivial zeros you said? There can be at most one. Yeah, this is my R. R can contain at most one trivial zero. And this trivial zero, we know where trivial zeros are. Okay, it is either here or here. Okay, it has to be to the left of 0, or so either at 0 or at -1. Okay. Is it clear why there will be one, at most one trivial zero in this? I mean, where are the trivial zeros of chi is primitive? So where are the trivial zeros? It's on this line. Yeah, it has to be on the x-axis, and on the negative part. So there's nowhere else, no other possibility. The only possibility by the creation of my rectangle is such that it is either at 0 or at -1. Well, okay. Now, now you can use the functional equation. You can use the functional equation, and so when chi -1 is equal to 1, then the completed function C S chi, this you remember, this is pi to the power minus s by 2, q to the power s by 2, gamma s by 2, and L S chi. All right? So that means that there are two on this contour. There are two parts which will have same number of zeros, right? If you consider any half of it, that's fine. All right. So so if I write, then you have a problem. Who has a problem, or who has a solution? So so this means that if I take 2 pi, and then that was my notation, n t chi plus 1, this from my functional equation, this will be equal to the half contour delta, half of this rectangle, and the argument of psi s chi. Okay. Is that what you wanted to do? You told me that you wanted. So now, how do you want to proceed now? What will happen? So this is true, okay, and so now chi of either chi of minus 1 is 1 or chi of minus 1 is minus 1. All right, that I know. And when chi of minus 1 is 1, I get this. Yeah. So if I move this by, if I use the functional equation, then delta argument of gamma s plus a by 2, this is equal to t log t by 2 minus t plus big O of 1. Yeah? Delta is the contour, okay? It's the contour of that rectangle, okay? And this little a, is either 0 or 1. A is 0 if chi minus 1 is 1, and it's 1 if chi minus 1 is equal to minus 1. So that's the case. Here I have chi minus 1 is equal to 1, and therefore I have used this. So chi minus 1 is 1, and this a here is equal to 0. So the argument of s by 2 I get from here, this is t log 2 plus this half. Okay? So log, here if I take, since I have an argument here, then you see delta, I can also take this to be the half contour instead of, because of symmetry, if I take from half minus it, okay, so let's take another color. Here, say half is here, okay. If I take half minus it to 5 by 2, okay, half minus it, so half is here, and I have my IT here. 5 by 2 minus IT. This is 5 by 2. This is here. Okay. Then from 5 by 2, take the symmetry here. Okay. This is possible because of this symmetry. Yeah. And now you know that log S chi is bounded by real S equal to half. So log S chi, no white. So log real S equal to half by 2. So this gives me the, yes, excuse me, log of A is what? Yeah. Here, are you talking about this? I didn't understand what you said. The pink line. Oh, what should the pink line be according to you? Ah, okay, okay. Yeah. Yes, of course. Yes. Because what you do is you move your rectangle to go now from half, instead of taking the first rectangle which you had, you go from half minus IT. So this is half minus IT here, okay? And to 5 by 2 minus IT, which is here, okay? And then from here you go up to 5 by 2 plus IT, where you were in the beginning, and then to half plus IT. So in fact, it has been, you have this is your new rectangle. And this is half of the contour, yeah, because the full contour, this was not symmetric. You had 5 by 2 on one side, and you had 3 by 2 on the other. So you make it symmetric, and this becomes your half contour, and then you bound it, and then it's fine. Okay. Good. Will you be able to write this for zeta? For zeta, what will be the difference? If you don't do this for if there's no chi in the story, I mean chi is 1, then what will be the difference? You can, everything's the same except that you can straight away begin with a smaller rectangle. Here I had to keep my -1 inside. Here, and for zeta, you can straight away begin with a smaller rectangle, and then you have your big you have your symmetry, and you have the limit. And instead of log L S chi, it will be log zeta S. That will be the only difference. It's actually just a question of copying and pasting more or less the proof. Okay, the number of zeros. Good. Now that you know so many things, now I'm going to ask you a little, this question is slightly harder. Okay, so if I assume the GRH, what happens? What is the GRH? The generalized Riemann hypothesis. Okay, assume the GRH try to write this for the Riemann zeta. Okay, just copy and see. Don't have to take such a big rectangle, take a smaller rectangle, and exactly the same thing will work. And yes, you want to integrate somewhere. Okay, so if you take it in a permitted area, that's fine. Okay, nobody is saying you have to stay in. I mean that you have to stay in that rectangle. You create the rectangle that helps you do it. Okay, so yeah, let's see if you can do this one. So assume the generalized Riemann hypothesis. Assume that the GRH is true. So GRH is true means what? What does this mean? It means that the non-trivial zeros of LS chi, the non-trivial zeros of LS chi should be where? Where should they be? S equal to half. Should lie on the line? Not should, they do, because I'm assuming it to be true. Lie on the line real S equal to half. Okay, assume this to be true. Now show that the explicit formula that we have found, this psi x chi, this is equal to big O of x to the power half log square qx. You can use the explicit formula that we found and see which part goes away if the Riemann hypothesis, generalized Riemann hypothesis is true. You also know the results for L prime by L and so on. Try to think about it for a while. You can use this NT chi. You may use this. NT chi is T by pi log Qt by 2 pi minus T by 2 pi plus big O of log Qt. Okay, so this is something you can use. And do you know what we can do with the sum of the zeros? If I take the sum of the zeros, and then of course I have to take these are non-trivial zeros. These are non-trivial zeros. Do you have any bound for this? Yes, they occur in conjugate pairs. So let's write gamma is equal to rho is equal to beta plus I gamma. Okay, and let's block this gamma somewhere, because of course like that we cannot find anything. Suppose I take this gamma to be less than something. So what would it be nice to have it to be less than? You see what I have here. This I have at x power half here. So if I take this to be less than x power half, then what should this be equal to? I mean, it will not be equal to anything. It should be estimated by something. What is the maximum that you can expect from here? You would like, yeah. What is the maximum? I mean, any bound will do. Tell me what kind of a bound you can expect here. So this will give me a log, right? And these rows are non-trivial zeros of LS chi. L has a conductor Q. So the Q has to show up somewhere. Yeah. So this is something like 1 by x. Okay. It's something like 1 by x. I'm taking the modulus of this. So the modulus of this is going to be beta square plus gamma square. Yeah. So modulus of this is to the half. These are real numbers, there's no problem. And this is to the half. So that means that I have a circle beta square plus gamma square, and I'm taking its square root. So what do I expect that should happen here? What should happen here is that I should get a logarithm. Yeah, I should get a logarithm, shouldn't I? I should get a logarithm of what? Of this is less than or equal to x to the half. Okay. So what do you expect? Log what log? Log of what? Qx. Yeah. What did you say? The Q. But the Q is the modulus. The Q will show up somewhere. These are not some random numbers. These are coming. This is a zero of L function whose conductor is Q. So the Q will turn up. It cannot be independent of the Q. Okay. But is it going to be log Qx? Is it going to be log Qx? This is half, but this is 1 upon this to the power half. So this will come 2 times. So you will get a log square. So at least these many terms will come up. All right? So there will be at least these many terms. So now you use partial summation. You can use a partial summation and this. Okay. Also, what you can use is something that we know, which we have seen in the previous courses, that L prime What do we know here? L prime is chi, L is chi. We've seen this several times. This is minus half log q by pi minus the relationship between gamma and, okay, this also you can use. Half log square x, you see that this occurs always under the Riemann hypothesis as well. If you assume the Riemann hypothesis, then what is pi of x? What is pi of x under the Riemann hypothesis? How can we express this? You have under Riemann hypothesis, if you have if the Riemann hypothesis is true, okay, so pi of x, I can write this as logarithmic integral logarithmic integral of x plus big O of something. Since now there are no zeros, non-trivial zeros, anywhere other than x half, so x half is coming up, and I have O x to the power half log x. Remember this? This O x to the power half log x always comes up for pi of x, psi of x, and no, there should be, no, that's okay, half log x. Yeah, so if you take instead of pi of x, if you take psi of x, or if you take tau of x like we did this morning, essentially the things will not change except the log x. Okay, only the log x might change. Okay, so that's a good hint. Now try to see what you can do now with this. A sheet of exercises, some supplementary exercises that you can try at home or at your leisure when you are. Okay, I think we don't do enough exercises. We do too much theory and not enough practice. I can make you a list of supplementary exercises which you can solve. Yeah. So will you solve this? I mean, I can do it tomorrow if you like. I can solve some more exercises tomorrow on this type. But otherwise, tomorrow what I wanted to do was, I wanted to do the Ternary-Goldbach problem with you. That is, you know, every integer, every Goldbach conjectured that you could write, yeah? What did he conjecture?
Sum of three primes.
3 primes, yeah? The 3 prime conjecture, and then there is a 2 prime conjecture. So the 3 prime conjecture has been solved the 2' conjecture has not been solved and is unlikely to be solved in the near future. So what I can do is I can explain the 3' conjecture to no, I can show you how we can use the sieve and the circle methods to do the 3' conjecture. That we can do tomorrow. Excuse me? No, not Helfgott's. Helfgott's proof includes a lot of computation. No, there are more classical ones. Helberg closed the gap. Okay. Oh, yeah. So yeah, if you know there are, I mean, Helfgott is a newly born person, so that's different. Whereas Vinogradov and Chen, they have older results on this, and I can show that to you tomorrow. So if I show you that tomorrow, then day after we can see what kind of questions are related to the binary Goldbach. I mean, that ternary does not imply binary. But okay, so don't believe that because the ternary can be done, the binary can be done. It's not really the same thing does not work. But we can look at this. I cannot do. You have something to say? No. You want to prove something? So that I can do in the next 2 days. So I don't know when I can do some more exercises of this type with you. Maybe tomorrow or may not. Or otherwise I'll give you some exercises, written exercises, and you can solve them. I'm not going to give you the solutions. I will only give you the exercises, yeah? And you can think about them, okay? And then we can continue tomorrow, all right? We can see how to do these.